Hey guys, how's it going? In this video, I'm gonna go through this problem from Pramp, largest smaller binary search tree key. Given a root of a BST and a target number is called num, we need to implement an efficient function find the largest smaller key, which is finds the largest key in the tree that is smaller than the target number. If such a number does not exist, just return the number -1, assuming all the keys in the tree are non-negative. So this already handle a lot of edge cases, which is good. We need to analyze the time and complexity as usual. Let's look at an example. Given a target number of 17 and a BST looks like this. We need to find the largest number that is smaller than 17. And the answer is 14. And why is 14? So we will be at the root node 20, which is greater than the target of 17. When it's greater, we go left, because the binary search tree on the left hand side is always smaller than the root node, and the right hand side is already bigger than the root node, so we go left. And when we are here, 17 is bigger than 9, right? So we go right? And then go to this branch, and then we ask ourselves 17 and 12, which one's bigger? So 17 is bigger, so 12 is too small, so we go right again. So we will arrive in here, and there's no more children. That's why we ended up in here, and that's the largest number that is smaller than 17. That's the answer. So also we have some constraints in here. So let's dive into the solution to this problem. And that is the function over here, and that's the function that we need to finish, right? So the function is called find largest smaller key, and so we are given a target, right? So the algorithm goes, so we have a variable named answer, so the answer is -1 to begin with. So once we found a smaller key, so we set the answer to be the bigger number of the current answer and the smaller key that we just found. Okay, so if the node's key is smaller than the target, and then that means the current node is too small, we go right. The right branch is always bigger than the root, right? That's the a property of the BST. At the same time, that we have found a potential answer, so we just update the answer by using this formula over here. And else, meaning that the key is greater than or even equal to the target, right? The node's value, the node's key is greater than or even equal to the target. That means the node is too big, so we go to the left branch, which will be smaller than the root node. And when we are in this the else statement, so we don't need to update the answer, because that's not a potential answer, because the key is simply too big. And yeah, and here you can see that this is little code for the implementation. So first we have the current node, right? We call it just look at the root node, right? So self.root, that's the current node, and also we have a initialization of the answer at the beginning gonna be -1, and while the current node is not none, and also if the current key is smaller than the target, right? So we'll be in this condition over here in this case. That means the current key is too small, we'll go to the right branch, right? So this is how we go to the right branch, right? And also we need to update the answer. That's exactly that, right? So this is exactly that, right? And so the next current node will come back to the while loop until it's none, right? This while loop will be finished until will not be finished until the current node is none, right? So on the flip side, when the current key is greater or equal to the target, which is in this case, we don't need to update the answer, and also we need to go left. Okay, and that's about it for this problem. But there's one little optimization that will allow us. So this solution will not yet give us the full score, because let's look at here. To get a full score for the problem solving, your peer must be able to explain why it is possible to always store the last key smaller than the target without comparing to the previously stored key. And we do compare it to the previously stored key, right? So that's why this solution may not be able to get us the perfect score. So there's a little optimization to do that, right? So we just simply just set, right? So instead of comparing, and we simply just set it to the current key. And why this work, right? So we don't need this one anymore, right? So this one will work. And why this will work? And the answer is here. So let me read it out loud for you. It's important to understand why we always store the last key without comparing to the value stored beforehand, right? If we have stored a key before, it means that we have chosen to continue down the key's right subtree. So we are going to the right branch, right? Therefore, all the subsequent key will be larger than any previously stored key. And what it means is that if we go back to this branch, right? If we are in, let's say, from 20 and go to the 9, and then we know that we go to the right branch, right? So anything in the right branch will be bigger than 9. So even the smallest guy, which is 11, it will be bigger than 9, right? So at the time when we decided to go to the right branch, we know that anything in the right branch is bigger than 9 anyways. So we don't need to compare. So it's the same logic to apply to any nodes in the BST, right? So by that logic, we don't need to do a comparison to all the previous key already, and that's the reason why. And for time complexity, it's gonna be a big of log n for a balanced tree. Otherwise, if the tree is extremely imbalanced, it will take up big of n. So if you ask me what's balanced and imbalanced BST, let me show you. And as you can see, so this one has only the right child node. This one is extreme imbalance. So this one we have to traverse all the nodes, right? So this one takes up big O of n, right? And this one is balanced. You can see there's a left child, and right child. And this is a balanced tree, and this is gonna take big O of log n for time complexity. And this is true for most of the BST problems. And for space complexity, it's going to be O1, right? So we only need one pointer to point to the current node and also save the answer right here. And I think we still need this guy over here. Yeah, so this is my solution to this problem. I hope you find this helpful. Thanks.